Yes, metal IT equipment enclosures, such as racks, should be grounded. There are several reasons for grounding. Firstly, electrical safety. Grounding provides a safe path for fault currents to flow, preventing shocks and electrical fires. Secondly, electrostatic discharge or ESD protection. Grounding dissipates electrostatic charges, reducing the risk of damage to sensitive electronic equipment. Thirdly, electromagnetic interference or EMI reduction. Grounding helps to minimize EMI, which can interfere with the operation of electronic devices. Fourthly, regulatory compliance. Most electrical codes require metal enclosures to be grounded for safety. There are a few exceptions to this rule. Firstly, floating racks. In some rare cases, where electrical isolation is required for specific equipment, a floating rack may be used. This involves isolating the rack from ground and using other means of ESD protection. Secondly, emergency generator power. When operating on emergency generator power, metal enclosures should be grounded to the generator ground. To ground metal IT equipment racks, connect them to firstly, the building ground. Connect the rack directly to the building's grounding system using a grounding wire and grounding rod. Secondly, a dedicated ground rod. Install a dedicated grounding rod for the rack and connect it to the rack enclosure. Thirdly, other grounded equipment. Connect the rack to another grounded metal object, such as a metal conduit or grounded cable tray. Here are some recommended practices. Use a low impedance grounding path, less than 10 ohms. Use number 6 AWG or larger copper wire for grounding connections. Inspect grounding connections regularly for looseness or corrosion. Consider using anti-static wrist straps and mats when handling sensitive electronic equipment. Grounding is a critical aspect of ensuring the safe and reliable operation of IT equipment. It protects personnel, prevents equipment damage, and minimizes interference. Following these guidelines will help to maintain a safe and efficient IT environment. When dealing with grounding systems, it's crucial to understand the principles of electrical safety and the potential hazards that can arise from improper grounding. A properly grounded system provides a low impedance path for fault currents, allowing protective devices like circuit breakers and fuses to quickly interrupt the circuit, preventing dangerous voltage levels from persisting on equipment enclosures. The concept of impedance is key to understanding grounding. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. A low impedance grounding path ensures that fault currents can flow easily back to the source, tripping the protective devices and clearing the fault. A high impedance ground, on the other hand, can limit the fault current, preventing the protective devices from operating and potentially leading to a dangerous buildup of voltage on the equipment. The use of number 6 AWG or larger copper wire for grounding connections is recommended because it provides a low impedance path and can handle the high fault currents that may occur during a short circuit. Copper is an excellent conductor of electricity, and its larger cross-sectional area reduces resistance. Other factors to consider when selecting grounding wire include its insulation type and its suitability for the environment in which it will be used. Regular inspection of grounding connections is essential to ensure that they remain tight and free from corrosion. Loose connections can increase resistance and reduce the effectiveness of the grounding system. Corrosion can also degrade the conductivity of the connections, leading to similar problems. When inspecting grounding connections, look for signs of rust, oxidation, or physical damage. Clean and tighten any loose connections and replace any corroded or damaged components. Anti-static wrist straps and mats are used to prevent electrostatic discharge or ESD, which can damage sensitive electronic components. ESD occurs when there is a buildup of static electricity on a person or object, and this charge is suddenly discharged to another object. The discharge can create a high voltage spark that can damage or destroy electronic components. Anti-static wrist straps and mats provide a path for static electricity to safely discharge to ground, preventing ESD events. The wrist strap should be worn snugly against the skin and connected to a grounded point. The mat should be placed on the work surface and also connected to ground. In addition to these practical considerations, it's also important to be aware of the relevant electrical codes and standards that govern grounding practices. The National Electrical Code, or NEC, is a widely adopted standard that provides detailed requirements for grounding and bonding electrical systems. It's important to consult the NEC and any other applicable local codes and standards to ensure that your grounding system is compliant. The NEC specifies requirements for grounding electrode systems, grounding conductors, and bonding conductors. It also provides guidelines for grounding specific types of equipment and systems. Understanding the NEC requirements is essential for designing and installing a safe and effective grounding system. Grounding electrodes are used to establish a connection to the earth, providing a path for fault currents to flow. The NEC specifies several types of grounding electrodes, including ground rods, ground plates, and metal underground water pipes. The selection of the appropriate grounding electrode depends on the soil conditions and the specific requirements of the installation. Grounding conductors are used to connect equipment enclosures and other metal parts to the grounding electrode. The NEC specifies the minimum size of grounding conductors based on the size of the overcurrent protection device in the circuit. Bonding conductors are used to connect different metal parts of a system together, ensuring that they are at the same electrical potential. This helps to prevent voltage differences that could create a shock hazard. The NEC also addresses the grounding of specific types of equipment such as transformers, generators, and motors. These types of equipment may have special grounding requirements that must be followed to ensure safety. In addition to the NEC, there are other standards and guidelines that provide information on grounding practices. The Institute of Electrical and Electronics Engineers, or IEE, publishes a number of standards related to grounding, including IEE Standard 142, also known as the Green Book, which provides recommended practices for grounding and bonding of electrical equipment. Effective grounding is a multifaceted topic that goes beyond simple connections. Firstly, understanding ground impedance is crucial. Ground impedance is the total opposition that the earth offers to the flow of current. A lower impedance means a more effective path for fault current. Soil composition, moisture content, and temperature affect impedance. Sandy soil, for example, has a higher impedance than clay soil. Secondly, ground resistance testing is important. Ground resistance testing measures the resistance of the grounding electrode to the earth. The fall-off potential method is a common technique using test stakes and a ground resistance meter. A low reading, ideally below 25 ohms as per the NEC, indicates a good ground connection. Thirdly, ground loop prevention is key. Ground loops occur when multiple ground paths exist, creating circulating currents that can cause noise and interference. Proper grounding design minimizes ground loops by ensuring a single, clear ground reference. Fourthly, static dissipation is a concern. Static electricity buildup can damage sensitive components. Grounding helps dissipate static charges safely. Anti-static mats and wrist straps are common solutions in environments with sensitive electronics. Fifthly, lightning protection is necessary. Lightning strikes can induce high voltage surges. Grounding is a critical component of a lightning protection system, diverting the current to the earth. Sixthly, equipment bonding is essential. Bonding ensures that all metal parts of a system are at the same electrical potential. This reduces shock hazards and minimizes electromagnetic interference. Seventhly, conduit grounding is important. Metal conduit should be properly grounded to provide a safe path for fault currents. Conduit grounding clamps and bushings ensure a secure connection. Eighthly, cable tray grounding is similar. Cable trays, like conduits, should be grounded to prevent shock hazards and reduce noise. Grounding straps or bonding jumpers connect cable trays to the grounding system. Ninthly, isolated ground systems are sometimes needed. Isolated ground systems minimize noise in sensitive equipment. They provide a separate grounding path that is isolated from the building's main ground. Tenthly, ground fault circuit interrupters or GFCIs add safety. GFCIs detect small imbalances in current and quickly interrupt the circuit, preventing electrical shock. They are commonly used in wet or damp locations. 11thly, surge protection devices or SPD are vital. SPD protects equipment from voltage surges caused by lightning or other electrical events. They divert excess voltage to ground, preventing damage to sensitive components. 12thly, grounding system design needs planning. Proper grounding system design considers the specific needs of the facility and equipment. Factors include soil conditions, equipment sensitivity, and applicable codes and standards. 13thly, regular inspections are necessary. Grounding systems should be regularly inspected to ensure that connections are tight and free from corrosion. Infrared thermography can detect hot spots caused by loose connections. 14thly, documentation is good practice. Maintaining accurate documentation of the grounding system is important for troubleshooting and maintenance. This includes grounding system diagrams and test results. 15thly, training is important. Personnel working with electrical equipment should be trained on proper grounding practices. This helps prevent accidents and ensures that the grounding system is properly maintained. 16thly, compliance with standards is essential. Grounding systems must comply with applicable codes and standards such as the NEC and IEE standards. This ensures safety and reliability. 17thly, understanding fault current paths is critical. Knowing how fault current flows through the grounding system is essential for troubleshooting problems and ensuring effective protection. 18thly, minimizing ground loops is important. Ground loops can cause noise and interference in sensitive equipment. Proper grounding design minimizes ground loops by providing a single, clear ground reference. 19thly, proper wire sizing is important. Using the correct size grounding wires is essential for carrying fault current safely. The NEC specifies minimum wire sizes based on the size of the overcurrent protection device. 20thly, using proper connectors is necessary. Use connectors that are specifically designed for grounding applications. These connectors provide a secure and reliable connection. 21stly, avoiding aluminum copper connections directly is important. Avoid direct connections between aluminum and copper grounding conductors, as this can lead to corrosion. Use listed bimetallic connectors when connecting dissimilar metals. 22ndly, maintaining a clean grounding environment is good practice. Keep the grounding environment clean and free from debris, as this can affect the performance of the grounding system. 23rdly, addressing corrosion prevention is key. Protect grounding connections from corrosion by using corrosion inhibitors or other protective coatings. 24thly, knowing about dedicated circuits is necessary. Use dedicated circuits for sensitive equipment to minimize noise and interference. This includes providing a separate grounding path for these circuits. 25thly, considering site-specific needs is always important. Grounding requirements vary depending on the specific site and equipment. Consider the unique needs of each installation when designing the grounding system. 26thly, understanding the role of bonding jumpers is essential. Bonding jumpers are used to connect metal parts of a system together, ensuring that they are at the same electrical potential. They are essential for preventing shock hazards. 27thly, using star grounding topologies is good practice. Star grounding topologies provide a single point of ground reference, minimizing ground loops and noise. 28thly, knowing the importance of high-frequency grounding is necessary. High-frequency grounding is important for sensitive electronic equipment that operates at high frequencies. It minimizes noise and interference. 29thly, utilizing grounding for shielding is important. Grounding can be used to shield sensitive equipment from electromagnetic interference. This involves enclosing the equipment in a grounded metal enclosure. 30thly, grounding for signal reference is necessary. Grounding provides a stable reference point for signal voltages. This is important for accurate signal transmission. 31stly, testing grounding electrode resistance regularly is important. Test grounding electrode resistance regularly to ensure that it remains within acceptable limits. This helps to ensure the effectiveness of the grounding system. 32ndly, conducting visual inspections periodically is good practice. Conduct visual inspections of the grounding system periodically to identify any signs of damage or corrosion. Thirdly, maintaining system records is essential. Maintain accurate records of the grounding system, including diagrams, test results, and maintenance records. Fourthly, following manufacturer recommendations is key. Follow the manufacturer's recommendations for grounding equipment. This helps to ensure that the equipment is properly grounded and protected. Fifthly, engaging qualified professionals is important. Engage qualified electrical professionals to design, install, and maintain the grounding system. This helps to ensure that the system is safe and effective. Understanding grounding principles is essential for electrical safety. Properly grounding equipment protects people from electric shock and prevents damage to equipment. It is important to follow established codes and standards and to consult with qualified professionals when necessary. The goal of grounding is to create a safe and reliable electrical system. Proper grounding ensures that fault currents have a low impedance path back to the source, causing protective devices to trip and clear the fault. This prevents dangerous voltage levels from persisting on equipment enclosures. Grounding also helps to minimize electromagnetic interference, which can disrupt the operation of sensitive electronic equipment. By following best practices for grounding, we can create a safer and more efficient electrical environment.